Welcome back to the Gaussian 16 series. Have you ever just stared at a computational chemistry setup screen totally overwhelmed, wondering which of those cryptic acronyms you're supposed to pick? Well, you are in exactly the right place. Today's explainer demystifies basis sets, showing you exactly how to choose the right one without just guessing. We're going to save you time, computational resources, and honestly, a whole lot of headaches.
We are absolutely thrilled to bring you this Foundation Number 2 explainer directly from the experts at VirtualChem Labs. They're basically the masters of breaking down complex quantum chemistry into actionable, practical steps. And today is all about building that rock-solid foundation for your research. Let's get right into it.
Okay, so let's clear up the most common point of confusion right out of the gate. Think of your computational setup in two distinct halves. On one side, we have your method. This is your model of electron correlation. It's how you treat those super complex interactions between electrons. But on the other side, we have the basis set, which is our main focus today. Your basis set dictates the actual physical quality of the orbital description in space. Both of these directly feed into your overall accuracy and computational cost, but they do completely different jobs.
Here's our roadmap for today. We'll quickly define what a basis set is, explore the three main upgrades, break down common families, walk through a practical decision tree, and finally, look at the big mistakes you need to avoid.
All right, section 1. What exactly is a basis set? Let's define our foundation.
In quantum chemistry, we simply can't solve the exact equations for complex molecules, so we have to build approximations. The crucial takeaway here is that a basis set is really just a collection of mathematical functions that we use to construct these approximate molecular orbitals. The more functions you have and the more flexible they are, the better your approximation is going to be. But of course, that always comes with a higher computational price tag.
Think of a basis set kind of like the resolution of an image or a video screen. If you use a low-resolution basis set, your orbital cloud looks blocky and pixelated. It's a rough, quick approximation. As you increase that basis set size, you get a higher resolution, smoother, and vastly more accurate orbital cloud. But just like a 4K video eats up way more space and processing power on your computer than a tiny low-res clip, a higher resolution basis set demands a lot more computational time.
Moving right along to section 2, the three upgrades. That's size, polarization, and diffuse functions.
So, every time you want a better, more accurate answer from Gaussian, you are usually adjusting one of these three levers. This is your essential toolkit triad: size, polarization, and diffuse functions. Let's break down exactly what each one of these does to your molecule.
First up is size, which you'll often hear referred to as split valence. Think about your valence electrons for a second, the ones actually out there doing the chemical bonding. In a split valence basis set, we describe these absolutely crucial valence orbitals using multiple sets of mathematical functions. By adding more functions, you're giving those valence orbitals way more flexibility to expand or contract. Moving up this ladder from a small to a medium to a large basis set generally improves your molecular geometries and your calculated energies. But again, remember the golden rule here: more flexibility always equals more cost.
Second, we have polarization functions. Imagine two atoms approaching each other to form a bond. Their electron clouds don't just stay perfectly spherical, right? They pull and stretch toward each other. Polarization functions allow for the specific shape flexibility. They let the electron density distort asymmetrically, which is entirely realistic and honestly necessary for chemical bonding. Without polarization functions, your atoms are stuck acting like rigid, unyielding spheres, and you'll end up with wildly unrealistic geometries and pretty terrible energetic predictions.
Third in our toolkit, we have diffuse functions. Now, while polarization changes the shape, diffuse functions change the sheer physical reach of the orbital. They extend that electron density much, much farther away from the nucleus. Why would we need this? Well, if you have an ion with a negative charge, those extra electrons actively repel each other and puff out the electron cloud significantly. Without diffuse functions, Gaussian simply cannot see that expanded cloud. They are an absolute necessity for modeling anions, Rydberg excited states, or any weak non-covalent interactions where that long-range charge distribution really matters.
All right, on to section 3, common basis set families. We're talking Poppel, Def2, and correlation-consistent sets.
Let's map out your main options here depending on what your goals are. First up, we have the Poppel basis sets, like 6-31GD. You will see these literally everywhere in textbooks. They're great for comparing with legacy data and for teaching, but they are a bit less systematic across the periodic table. Next is the def2 family. Listen, if you take away just one practical tip today, make it this. The def2 family is an incredibly strong modern default, especially if you're running density functional theory or DFT workflows. It's highly systematic across the elements and just a fantastic starting point. Finally, we have the correlation consistent sets like CCP-BDZ or VTZ. If you are running high-level wave function methods like coupled cluster and you really need systematic convergence for rigorous benchmarking, this is the family you want to use.
Now for Section 4, the practical decision tree. Let's talk about how to actually choose.
Let's start with the most common scenario you'll probably face. What if you're simply doing routine geometry optimizations and frequency calculations on neutral organic molecules or main group elements? What should your go-to choice actually be? For these routine, day-to-day jobs, please don't overcomplicate it. You'll want to start with a medium-sized basis set that inherently includes polarization functions. Because remember, we need that shape flexibility for realistic bonds. A really great example would be something like def2-SVP. Then, once your geometry is fully optimized, if you find you need highly accurate final energies, just take that optimized structure and run a single-point energy calculation, stepping up to a larger triple zeta quality basis set like def2-TZVP. Easy.
But what if we change the scenario? What if your specific system is an anion, or it relies on strong hydrogen bonding, involves weak van der Waals interactions, or maybe you're looking at excited charge transfer states? In every single one of those cases, you absolutely must use diffuse functions. Seriously, if you forget them, the software simply won't have the mathematical language to describe electron density that's far out from the nucleus. You risk massively underestimating the binding energy of weak complexes, or worse, you could end up with highly unstable and completely nonsensical electronic solutions. Always remember, expanded clouds require diffuse functions.
Finally, let's look at the heavyweights. Are you calculating heavier elements way down the periodic table, or perhaps transition metals right smack in the middle of the D block?
For these heavier atoms, the sheer number of core electrons makes the computational cost just skyrocket, and relativistic effects actually start to matter. Here, your choice becomes hypercritical. You're likely going to need to incorporate effective core potentials, or ECPs. Think of these as a clever mathematical shortcut. They replace the computationally heavy, non-reacting core electrons with a simplified potential. This allows you to focus all your precious computational power on the valence electrons that are actually doing the chemistry. Families like diff2 are fantastic here because they pair cleanly and seamlessly with these potentials.
Okay, home stretch. Section 5, common mistakes. Here is what you need to avoid.
I'm totally serious. You might want to print this checklist out and tape it next to your monitor. Avoid these classic errors. First, never use a tiny basis set for your final reported energies and claim high accuracy. It just doesn't work that way. Second, like we just stressed, never forget those diffuse functions for anions or weak interactions. Third, don't blindly compare energies across calculations that use different basis sets. The underlying mathematical foundations are different, so the absolute energies just aren't directly comparable. Fourth, please don't mix and match different basis sets across different atoms in a molecule without a very specific, well-understood protocol. And finally, perhaps the most important one of all, sometimes a failing calculation is not the basis set's fault. If your method fundamentally fails to capture the chemistry of your system, upgrading to a massive basis set won't fix it. It's literally just going to give you the wrong answer but slower.
Thank you so much for joining this VirtualChem Labs explainer. We have officially conquered the right side of our initial diagram, the basis sets. Be sure to check out virtualchemlabs.com for some incredible workshops, resources, and hands-on learning. Next time, we're going to tackle the left side of that diagram, methods in Gaussian 16. We're talking everything from Hartree-Fock to DFT, MP2, and coupled cluster. But until then, I want to leave you with a provocative thought to ponder today. Look at your most recent calculation. Are you entirely sure you didn't just spend 48 hours computing an artifact of a missing polarization function? Choose your basis sets wisely and keep exploring.